final presentation of this session. We have Babak Ehsani. Welcome. We are going about optimization in buildings, and if I understand correctly, we're looking a little bit how to think of optimizing spaces just on how people are interacting in them, right?
Yeah, that's correct.
All right.
Okay. Good morning, everyone, and thank you for being here. My name is Babak Ehsani, and I am a PhD researcher in Istanbul Aydın University in Turkey. And today I will present my research titled Data-Driven Spatial Optimization in Smart Building Using Digital Twin Feedback Loops and AI Simulation. This research explores how digital technology and artificial intelligence can help building adapt to constantly changing needs of their occupants. In particular, the study investigates how digital twin system combined with AI simulation can support dynamic spatial optimization inside the smart buildings. To begin, I would like to highlight a fundamental paradox in architecture. Most buildings are designed to last for 40 to 50 years. However, the way we actually use this building changes much more quickly. Work pattern, organizational structure, collaboration style, and even technological tools evolve every few years. As a result, space that were optimized during the design stage often become inefficient or uncomfortable over time. In other words, we design building as a static object, but human activity inside them are highly dynamic. When problems emerge, we usually attribute them to mechanical systems such as HVAC, performance or lighting condition. However, in many cases or many scenarios, the real issue is not the building system themselves, but rather than a special configuration of the environment. Here, this raises an important question: how can building become more responsive to changing human needs? This question formed the starting point of this research. The objective of the study is to explore how building evolve from a static container into adaptive environment. Instead of treating spatial design as a one-time decision made during the design phase, we propose a system where spatial configuration can be continuously evaluated and improved throughout the building life cycle. To achieve this, the research introduced a framework that integrates two emerging technologies: digital twin system and generative artificial intelligence. The key idea is to close this loop, feedback loop, between the real-world building data and computational spatial optimization. Let us now look at the proposed framework. The architecture of the system is organized into three interconnected layers. The first layer is a physical layer, and this layer represents the actual building environment, including IoT sensors installed throughout the whole building. These sensors collect the real-time data about environmental and behavioral conditions, such as occupancy level, acoustic condition, and also thermal comfort. And the second layer is digital twin. The digital twin acts as a real-time virtual representing of the building. It continuously receives and processes data from the physical environment and updates digital model accordingly. In other words, it functions as a dynamic mirror of the building. The third layer is AI agent, which act as an analytical and decision-making component of the system. Within this layer, we apply deep reinforcement learning techniques to simulate potential spatial change and evaluate their performance. Throughout this architecture, the system becomes capable of analyzing spatial condition and exploring alternative configuration computationally. The core innovation of the proposed framework lies in what we call digital twin feedback loops. In many current implementations, digital twin systems function primarily as just like monitoring dashboard. They visualize environmental data, but they do not actively participate in decision making. In contrast, our framework transfers the digital twin into active optimizing system. The AI agent continuously evaluates a spatial condition and asks a simple but powerful question. What would happen if the spatial layout were adjusted? To answer this question, the system runs thousands of simulations within digital environment. Different spatial scenarios are tested, including variation in furniture arrangement, zoning strategy, and circulation pattern. Because all these experiments occur inside the digital model, they can perform without disrupting the real building environment. And through this iterative simulation process, the system can identify configuration that improve both environmental performance and occupant comfort. From a technical perspective, the framework bridges the gap between the building information modeling and artificial intelligence. The geometry and spatial structure of the building is represented using BIM model created in a Revit, which provide the static geometry and a special relationship required for simulation. Python scripting is used to manage the data pipeline, integrated sensor information, and control the simulation process. The system is deployed on a cloud-based infrastructure using Microsoft Azure, which enable real-time data ingestion, scalable storage, and continuous integration of IoT sensors streamed within the digital twin environment. Finally, the machine learning component is implemented using TensorFlow, where a reinforcement learning agent is trained to evaluate and optimize spatial configuration. Together, these technologies create an workflow in which building data, a spatial model, and AI algorithm operate within a unified computational environment. Before applying AI simulation, it's important to understand what type of data drive the system. The simulation model relies on a multiple data source. These include occupancy pattern, environmental condition, spatial contrast, and behavioral usage data. Together, these data sets allow the system to replicate the real operation conditional inside the building. This data-driven foundation enables the AI agent to evaluate spatial performance more accurately. At this point, the important question arises: is AI-based spatial optimization actually feasible in real architectural practices? To explore this question, we can examine one of the most influential industry examples in this field. The project is Autodesk Mars office in Toronto. In this project, Autodesk applied generative design techniques to optimize the spatial layout of their office environment. As you watch this short video, notice how design process is treated not simply as a drawing plan, but as solving a computational optimizing problem. In this project, Autodesk collected detailed information from approximately 250 employees, and they collected data including several types of spatial preference, for example, adjacency relationships, and identify which team needs collaborate frequently, and they also collected information about acoustic preference and distinguishing between employees who require a quiet environment and those working in a collaborative settings. Additionally, daylight access and environmental comfort preference were included in a dataset. All these parameters were translated into computational constraint and objective. Using the parameter, the generative design produced approximately 10,000 different spatial configurations. Each configuration was evaluated against multiple preference criteria. The algorithm had to balance competing goals such as spatial density, access to daylight, privacy requirements, and collaborative proximity. These processes demonstrate how artificial intelligence can explore a design space for larger what is typically possible through a manual design iteration. The result is a set of optimized spatial layouts generated through computational exploration. However, these optimizations happened before the building was actually used. However, this example also revealed an important limitation. The optimization process in Autodesk project occurred only once before the office was built. After construction, the spatial layouts remain relatively fixed, and our research proposed the next step in this evolution. Instead of performing spatial optimization only during the design phase, we propose a system capable of continuous optimization throughout the building life cycle. And by integrating digital twin and AI simulation, the system can repeatedly evaluate a spatial condition as the organizational pattern evolves. This enables building to respond to change in occupancy, work pattern, and environmental condition over time. Simulation result, and to test feasibility of this approach, we conducted a predictive simulated based on a typical open plan floor office. Within the simulation environment, the AI agent evaluates multiple spatial configurations while considering environmental condition and occupant distribution. Based on simulated 3 months evaluation period in a controlled digital twin environment, the results suggested several potential improvements compared to the baseline configuration. The results indicate notable improvement in energy performance and occupant comfort. This improvement was primarily associated with optimizing spatial density in relation to daylight availability. Although these results are based on a simulation, they suggest that spatial optimization can significantly influence both environmental performance and user satisfaction. Despite this promising result, several challenges remain. One of the most important issues concerns about human agency. If an algorithm suggests moving furniture or reorganizing a spatial zone, how much control should occupant have over these decisions? Our findings indicate that the system should not operate as a fully automated mechanism. Instead, it should function as a decision support system for facility manager and designers. In this model, the AI provides recommendation and analytical insight while human stakeholders retain final decision-making authority. To conclude, the future of the smart building may not depend solely on improving mechanical system or energy technology. Equally important is the ability of the building to adapt spatiality to human needs. By integrating digital twin feedback loops with AI-driven simulation, we can move toward a new generation of built environment that continuously learn from data and evolve over time. Such adaptive environments have a potential to improve energy efficiency, spatial performance, and occupant well-being simultaneously. To wrap up, we believe that the true intelligence of a smart building lies not just in its sensors, but its ability to adopt the people inside. Thank you very much for your time and attention.
Thank you very much.
You're welcome.
See you. Any questions starting from the audience? I'll start with a few very interesting outcomes there. I'd be interested, first of all, did you find during this research some common things, that what are like the lowest hanging fruits when you see from the data that would improve the well-being of people in the spaces?
Of course, because